Thank you. I'm going to first acknowledge a student that is working on this, Reza Nazuri, as well as a young faculty member, Arturo Montoya, that we brought into the project recently, and my co-investigator, Fred Testic, who's a fluid dynamics expert. One of the things I've done in my career is I've had the chance to work in earthquake engineering and do field inspection. And so remember, this was many years ago after an earthquake had happened in Peru. I went there and they built their houses with adobe, and of course a lot of people have died after the adobe houses collapsed. And I couldn't help but notice that people were picking the adobe blocks from the collapsed houses and building their houses again using the same materials and the same methods. A few years later, I was in Bingöl, Turkey, and I had the same experience. There were, evidently there were construction methods and materials that were deficient. And you walk down the street 5 days after the earthquake and they're continuing their construction with the same methods and the same techniques. Okay? So that's, you think that that happens in rural Peru and that happens in rural Turkey. The motivation for the study is that when we had the experience with Hurricane Katrina, we got hit pretty hard in our bridge infrastructures. By estimates of how much it costs to repair those bridges or replace them, in many instances, was upwards of $1 billion. And when we think about it, I think that we're following the same approach that people in rural Turkey and people in rural Peru are following, in that we're rebuilding our infrastructure. Maybe, you know, we looked around and some people made empirical observations of what worked and what not worked so well. So maybe we're doing a little bit better, but we haven't adopted a systematic approach to learn and to estimate the risk and to make more risk-informed decisions. And that's the motivation for this project. So when a hurricane attacks a bridge, impacts a bridge, it generates horizontal forces and it generates uplift forces, and they're very simple equations that are used today to estimate that. Of course, the limitation of predictive approaches is that they don't tell you what can you expect in terms of damage. Will the bridge be damaged? Will it not be damaged? Will it be functional? Would it have to be shut down for 10 days, 20 days? So I think as we progress and we try to make more informed decisions, we need tools that we can use to be able to make estimates, scenarios of what's going to happen under different hurricane conditions. One of the biggest problems that we had in Katrina was the fact that the bridge superstructures were unseated. That, of course, leads to observing the properties of the bridge connections, and there was damage and unseating in bridges that had a multitude of different support conditions. So some of them were integral, and the forces were so strong that they managed to destroy the integral connection. They damaged it. So the fact that we can't approach this and say, let's just put shear keys in every bridge and that's going to fix the problem, because we have evidence to the contrary. So what are we trying to do? We're trying to develop a high-resolution model. Means we're going to use newer, more sophisticated techniques to develop a model where we can simulate a bridge under hurricane attack and try to understand what happens to it, not only when the bridge is in this pristine condition, but also as the damage progresses, so we can estimate different scenarios of damage. This is the very step, if you wish, in the process of thinking of this problem as a resiliency problem. We need to be able to have models that tell us what level of damage is going to occur depending on what we do with the bridge. So as far as this project goes, this is a very lofty, big problem. We can't tackle it in a year. We chose a very, very small subset of this problem. And as I was mentioning, we're trying to use new methods, multi-physics methods that deal with fluid dynamics and understand structures. We're creating these models, and we're trying to then use them to calibrate the behavior of these models using experiments that have been conducted. This one is an experiment that was conducted in the Oregon State Tsunami Basin. And then finally, the ulterior goal is to be able to do what I just described, is create different scenarios for hurricane conditions that we can impose on prototypical bridge structures. We can look at different bridge geometries. We can look at different support conditions and understand what are the probabilities of damage for each one of those, which ones are more resilient. Is there a way to reduce $1 billion worth of damage in a future hurricane like Katrina? So these are a couple of techniques that we focused on. The first one is coupled Eulerian-Lagrangian analysis. People in the finite element industry are beginning to use this in a smaller scale. The other one is smooth particle hydrodynamics. When we started the project, we were open-minded. We were trying to look at which one. They each have their benefits and their costs. And the software and the knowledge is a little bit more mature in the one on the left. So we got started with that one. And what we mean by coupled Eulerian-Lagrangian approach is that in structural analysis, which is my field, we typically use Lagrangian meshes. We create a mesh that has its nodes, and when we apply stresses or forces, the mesh deforms. So we track the deformation that goes between the undeformed state and the deformed state. Eulerian mesh is a different animal, it's a different beast. In this case, we create the mesh, but the material doesn't deform, the material moves. And so what we track is the flow of the material through the mesh, as opposed to tracking the way in which the material deforms. And of course, there are differences between the two. One of them, as I mentioned, we have nodes that move, and the other one, the nodes are fixed. In this one, the material stays put. In this one, the material flows. There are issues regarding the computational cost and suitability. For example, boundary conditions is very straightforward to define the boundary condition on a Lagrangian mesh. We know that the element is fixed. There's no changing that. When we deal with Eulerian meshes, we deal with conditions like inlets and outlets of fluid, and it becomes a much more complex problem to define the boundary conditions problem. Of course, there's on the other side of that, if we get severe mesh distortions in a Lagrangian mesh, it's a solid distorts too much, then we get bad numerical problems. And that is not a problem for the Eulerian meshes, and that's why we like them for fluids. What we're trying to do is to integrate these two, get them to coexist and act together. So this gives an example of a solution. One of the models that we run where the fluid interacts, but the equations of equilibrium and the equations of state of the fluid are solved simultaneously, and one informs the other. So they're interacting. The two types of meshes are interacting throughout the solution. Okay, so first stab at this is to begin to get a handle on applying these methods to the bridge problem and to the wave impact problem in bridges more specifically. So we started very simple models because we're concerned about things like generating the right wave shapes, the right wave amplitudes, wave velocities, making sure that we got inlet and outlet conditions simulated properly, and of course that we get an accurate representation of the fluid structure interaction. The water impacts the girder, it needs to find a path around it, it can't go through it. Then from my colleague who works in fluid dynamics is looking at the turbulent flow around the girder to make sure that's a suitable and reasonable solution. And last but not least, these are methods that are very computationally expensive. So to give you an idea, when we first got started, it would take us approximately 7 days to run one of our models. We're down to optimizing them to about 1 day of running. So as I mentioned, some of the complexities that we face, we modeled the Eulerian fluid. We need to define regions in which there's going to be water, regions in which there's going to be void, and the boundary conditions need to be defined correctly. As I mentioned, in the Lagrangian world, we think in terms of equilibrium equation. When we talk about fluids, we work in terms of equations of state. And we need to be very mindful, of course, of the different types of contact interaction between the two to make sure that they're simulated properly. Okay, so other than that, we define material properties. In this case, for concrete, for the girder, water, and water density and viscosity are important properties. In concrete, we think in terms of Young's modulus and Poisson's ratio. So first stab at the problem is just to be able to simulate waves to make sure that we have the right height and frequency, that we're imposing our boundary conditions correctly. And then we begin to work on the concept of embedding solids in that Eulerian mesh, which you can see done here, and looking at the interaction between the two. What happens when the wave impacts? This gives more of a progression. We want to make sure, for example, that the water, when it hits the girder, goes around in this case, and it creates then an area behind the girder where there is a void. Okay, so some of the things that concern us is, for example, simulating the velocity. You can see here what's happening with the fluid. And then, of course, there is the other side, which is what's happening in the girder itself. So we track stresses and make sure that we get reasonable results. And at the present time, we're working on calibrating. As I mentioned, there are a couple of experiments. One was a platform problem that was performed in 1969 by French in a wave tank. So there were a couple of variations of that. The other one, as I mentioned, is the tsunami basin in Oregon State with the wall. So we're trying to track the shape of the wave as it progresses to the wave tank and then the forces in the wall. And to conclude, once we get all these pieces together, our goal is to develop fragility relationships like the one that I'm showing here. This is for a different problem. But we would then identify some sort of intensity measure for the waves, and then probability of exceeding a certain damage state. In this case, we have 3 different damage states. And that we can use as the basis to study the resiliency problem on a more informed basis. So with that, I'll conclude. I'd like to acknowledge the support from Tran-SET for this project, and I'll welcome any questions that you might have.